So, as I said, that today our topic is on the MOS capacitor, and the MOS stands for metal oxide semiconductor, which is a particular focus on its with a structure. We will with a particular focus on this structure, we will progress through this course. So what we will study at first, we will study the key features, gate electrode evolution and their applications, and then we will see how the insulating layer, which is in present days mostly the high K material, and their properties affect the structure's performance or the characteristics. So to start with the definition, as I said, the MOS stands for metal oxide semiconductor devices. It has mostly three components that is a semiconducting substrate as shown here, then an oxide and a metal layer or the gate. So typically the semiconducting substrate is usually silicon, and there are others like germanium and many others, and also there are some recent trends on these metal oxide semiconductor and 2D channel materials, but the mostly still today is used, the one is used is silicon. And the insulating layer, previously it was silicon dioxide, but now we have moved to many different high K material, and hafnium oxide is one of them. It plays a crucial role in the device's functionality, and one of the key features of this structure is that we need very thin insulating layer. This thin oxide layer is much essential to ensure the efficient charge control, and it allows device to operate at much lower voltage, which is also crucial for modern electronic applications. Now, if we see the evolution of the gate electrode in MOS capacitors, before 1970s, metal gates like aluminum were primarily used. However, later we moved to the heavily doped polysilicon. We saw the significant improvement in thermal stability, which became increasingly important as the device scaling continued. Then after 2008, there was a notable shift back to using the metal gate, along with the introduction of this high K dielectrics here, which is famously known as high K metal gate technology. So this transition allowed for improved capacitance and reduced power consumption. It also enabled the continued miniaturization or the scaling of these semiconductor devices. And that's how we are today in our high K metal gate technology. So now let's look at the applications of these MOS capacitors. While they are not commonly used as the standalone devices, they are integral to functioning to gauge the functionality of the MOSFET or MOS transistors, which is mostly used in which is the most widely used semiconductor devices in modern electronics. The key developments in this area include transition from traditional silicon dioxide to high K dielectrics and reintroduction of the metal gate in the advanced technology. These kind of advancements, they have created the way for more efficient and powerful electronic components. Now, if we summarize this slide, so MOS capacitor is a functional element in semiconductor technology. Its structure, key features, and the evolution of the gate electrode reflect the ongoing innovations that have shaped the modern electronics. And it may not be directly used in the as a semiconductor component, but it is something very much fundamental we would like to understand in detail so that we can understand what kind of devices, the structure and the geometry we would be able to use in the modern semiconductor technology ICs. One of the powerful tool to judge the um, or to understand the physics of this MOS capacitor is the band diagram. The energy band diagram that you guys have already studied before in many other courses. So we will go much details into this energy band diagram of this MOS capacitor. But before that, I'd like to tell you one thing, that the contents of these courses will be taken from this book by Chen Ming Hu, and this is a very well written book, and there are many other books that are there, like Streetman Banerjee, Nieman. So please feel free to follow whatever you want. It's not a problem, but for me, I will be making the contents from this book, and um, if you have any questions, please feel free to ask. So whatever it is, whatever book you follow, we can tell that for the MOS capacitors, it's a custom to draw the band diagram in such a way that our MOS capacitor is arranged in this way. This might look like top, but it is not. This is the top and this is the bottom, at least in the traditional semiconductor front end of line. So we will be using this middle layer to denote the oxide or the insulating layer. The semiconducting layer's band diagram is on the right side, and on the left side is the metal. Yeah, so when we study this MOS capacitor, it's always good or convenient to first understand the energy band diagram for a special condition called the flat band voltage. So what is exactly this flat band voltage is? This is something that you can see here. All these bands are flat, so there is no curve or no bending over here. And how do we achieve it? So if you have a p-type body, then you apply a negative voltage over here. So as you know that the negative voltage will pull the band upward in the upward directions. So the band which were initially tilted like this, our band was tilted in our previous diagram you saw. It was tilted like that, and from the silicon it had slight bending. So they will be pulled upwards. And there are a few terms that we would like to learn here. So the first thing is that you have to also understand that as this band is in the flat band condition, so the electric field in the surface here is zero. There is no voltage drop here. Also, the electric field across the oxide is also zero. That's why the band is flat. If there is some voltage drop or electric field drop across there, the band won't be flat. So you can see this is the conduction band, this is the valence band, and this is the Fermi level. And the energy gap, this is called the energy gap. And the energy gap of SiO2 is 9 electron volt. And for metal, EC and EF lies at the same place. So there is another level that is called the E0, that is the vacuum level. So vacuum level is the energy of the electrons outside of this material. So if any electron crosses the conduction band, it's very easy to reach the vacuum level. I mean, the difference is very small here. However, the difference is around 4.05 I think how much is it? It's 4.05 volt for this silicon, and the difference is called the electron affinity. This is just another material parameter, just like this energy band gap. So you have to understand one thing, that E0, it must be continuous across the any interface. So this is also valid for Si-SiO2 interface. The conduction band of SiO2 here, this is 3.1 electron volt higher than that of silicon. This 3.1 electron volt is called the energy barrier, electron energy barrier. And then what is the hole energy barrier? So hole energy barrier is the difference from valence band to valence band. So you can see that it has such a large energy barriers, and this is why the electrons and holes cannot normally pass through the SiO2 get dielectric. And for the polysilicon here, this EC is also lower by 3.1 electron volt from SiO2. And as I told that the EF, the Fermi level and conduction level of N plus polysilicon, we can assume that they are in the same level, or they are coinciding for the simplicity. And to be honest, in SiO2, you can see there is no Fermi level here, and it doesn't really have any significance. Now, if we place somewhere here, this, let's say in the middle, if we place the EF somewhere in the middle, so what will happen? So the number of carriers will be very small. It will be approximately, how do we get the number of carriers? So it will be approximately 10 to the power 60 minus 60. And how do we get it? We get it by N of C and then exponent of EC minus EF by KT. This is, so as this value is too high, then we will get very low number of carrier concentration. So that's why it doesn't make sense. And there is one thing, that two terminology that you have to understand, the difference of EC from its respective vacuum level and from the EF to its respective vacuum level. It is EC here because we are assuming for the N plus polysilicon, EF and EC are at the same level. So this is called the work function. And the flat band voltage, VFB, this is just the difference of this work function. And that's all. So if you are given any MOS capacitor and you want to denote the flat band voltage, and this is basically just the difference between these two parameters. What will happen if we apply a voltage that is negative, a small negative voltage, which is just the difference between two work functions. Now what if we increase the negative voltage? So once we increase the negative voltage, you can see this, we are applying negative voltage here in the gate terminal. So the band on the left hand side will get will be raised upwards in the upward directions, will be pushed upward, and this is the result. And I always mention here whenever teaching this thing that you can also apply the same technique when you are writing some papers, that these band diagrams that we draw mostly are qualitatively. You cannot scale it. You can have the values, but you cannot always scale it because it will go beyond the page limit. So anyway, now when the Vg is much less than the flat band voltage, then we have some surface voltage here, and that is given by phi of s surface voltage, and also we will have some voltage across the oxide, which was 0 in our previous case, but now it is not anymore 0. And the band bending is upwards because the voltage is negative on the in the gate for p type or n type, whatever it is. I mean, if you apply voltage, it will go upward. Negative voltage, it will go upward. Now if my EC is also going upward, that means my surface voltage is also negative, and it will be positive if it bends downward. However, for here, um, it is negative as we applied the negative voltage here. So if you have trouble understanding the wave, the band is bending, whether it's moving, it's being pushed upward or downwards, you need to revise the previous some basics of this semiconductor device physics, which I believe it's not the scope of this class. So now if I apply a negative voltage here, so what will happen? It's a very gross or very not gross, very gross is a bad word to say. I would say very not very quantitative. We can think it in a qualitative way, that if I apply negative voltage here, I will have positive charges here, and then I will have negative charges here because it's a dipole. It's an insulating layer. So if you also are not aware of how these insulators work or what happens inside the dielectric, I suggest you read Feynman's lectures, maybe in the chapter 10 or 11 in the second part of that book. So now if it is negative here, you will have the positive sign or positive charged carriers over here. That is, the whole will get accumulated over here. So that's how we can say that this accumulation term is coming from, that holes are getting accumulated in the surface. So now if we are trying to denote how much our surface accumulation is, we get it by this it went far too long, it became, so it can be given by this equation. Now what can be the value of this surface potential? Typically it is around 100 to 200 millivolt negative. So negative 100 to 200 millivolt. So in that case, in that scenario, our surface accumulation will be much higher than the Na. So there are a large number of holes that is getting accumulated near the surface, and they will form an accumulation layer over here of positive charge. So this accumulation layer of charges we can denote by the accumulation charge. So what is the amount of charge that is getting accumulated, that we want to know. Now what is the applied voltage here? So previously in the surface, in the flat band condition, I had, so we just use the KVL, Kirchhoff's voltage law. We had the flat band voltage. Now I applied some extra voltage in the gate, and that extra voltage has been reflected in my oxide and in my semiconductor. So my surface voltage and the oxide voltage. And what is the oxide voltage? The oxide voltage can be given by Vg minus Vfb if for the first order model of the surface accumulation, we can ignore this value of surface potential because it is not very high. So this is more appropriate to say it approximately, but we can definitely say equal, as it is written in the book by Chen Minghu. I do not have the audacity to change it, but I can what I can say is that you can also try to do that, but typically it doesn't really matter whether you write it approximate or equal. You can ignore the phi s for the first order models. So in this scenario, so what will be our EOX, that is the electric field across the oxide, that is the charge accumulated here, because we have to create the balance in the charge. So the charge accumulated here divided by epsilon. And how do we get it? Using the Gauss law. We get it by Gauss law. Sorry, this thing is my pen is not really well because I'm using mouse. I don't have the pen and touchpad today. And then this thickness of this oxide is TOX. Then we can write the voltage drop is across the oxide. This is the voltage drop across the oxide layer. It is equal to electric field across the oxide multiplied by the thickness, and that can be given by this equation. And COX come from the parallel plate capacitance, C equal to epsilon A by D. Then you may ask that where is the area factor? So if you divide this by the area factor, so COX is capacitance per area. So from here you get the accumulation charge per area. Now what we get, that the VOX, the voltage drop, what is that? This is the substrate charge that is being accumulated here, and that is divided by this, because this accumulation charge is equal to substrate charge typically, or when we have flat band condition, we do not have any accumulation charge. So the accumulation charge is also accompanied by the substrate charge. So the substrate charge, it can take care of all the charges, all the charges that may be present in this substrate, including accumulation. So the drop across the oxide can be simplified and written as the substrate charge divided by the capacitance of this oxide. And you have to remember that this capacitance is the capacitance per area. Well, so what previously we were discussing was, if we apply negative voltage in a MOS capacitor with p-type substrate, what will happen? So now, as we saw, there is a condition called flat band voltage, and then there is a condition called surface accumulation, which is obtained when the negative voltage exceeds the flat band voltage. Now what will happen if we apply a more positive voltage, and the positive voltage is greater than the flat band voltage? So as we know, the positive voltage will pull down the band. So the left hand side here will be pulled down. So what is the amount it will be pulled down? It will be pulled down by the amount of voltage drop or the electric field across the oxide. And similarly, we will also see some kind of surface potential across the silicon. So in this case also, the oxide has some electric field, and also the silicon substrate surface also has some electric field. So this is called the depletion. So why? Because he applies some positive voltage here. So again, we can do that calculation that we did before. This will be negative charge area, this surface, and then this will be positive, and again hence here we will be slightly negative charged carriers, minority carriers. So this depletion. This is called the depletion of uh, majority carrier, and it has some width, and that is the depletion region width. So we want to know that how much is the depletion region width and how much is the voltage here. Yeah, so we want to know that how much is the uh, depletion region width and what is the applied Vg. So this condition. So first we know the VOX, the oxide voltage, is the total substrate voltage divided by the COX, and this is true for most of the conditions. So now the substrate charge is equal to the depletion charge, and from our previous learning we know that this can be the this is the equation of the depletion charge, and which can be further extended, and then we can see that we have some kind of surface potential which is given by this term here. So depletion charge here, it's a negative charge. So after accepting that extra electrons, they're negatively charged. And depletion region equation you can find in this book in maybe chapter 2 or 3, I forgot, but you can have a look into it. What is the equation of depletion region? And if we use that equation here, we get this voltage drop equation. So what is the total voltage drop or total voltage applied? And the total voltage applied will be summation of flat band voltage, because initially we had some sort of band bending, and so we need the flat band voltage to flatten it, and then we will have these surface potential and then the total voltage across the oxide. So that's my total voltage applied for the depletion condition. Now we will see what will happen if we further increase the voltage, the positive voltage. Well, okay, let's now focus on the other condition that's called threshold. And what is threshold condition? So what happens when we increase the get voltage beyond the depletion region? So if we keep on increasing the voltage, so the electron concentration over here will keep on increasing up to a certain limit. And when this surface electron condition becomes equal to the bulk hole condition, given that this is p-type, this is p body substrate, not p-type semiconductor, this is p-type semiconductor or p body substrate, not p-type MOS. So I have seen many of you are coming from different backgrounds, so I'd like to reiterate this again and again. For a n-type MOS we have p-type substrate. For a p-type MOS we have n-type substrate. So for the p-type substrate, that is n-type MOS, so p-type substrate, and that is n-MOS. If I increase the gate voltage positively, there will be a time, or there will be a point when this surface electron concentration will be equal to the bulk hole concentration. So that is what we call the threshold condition. Now let's draw a draw a line which is the middle, in the middle of the EC and EF. So it's middle throughout over here. So now there is a dip. This is Fermi level. So there's a dip of this or pulling up downward bending of this EC and EV. And if my surface electron condition is equal to bulk hole condition, so the difference between the conduction band here from the Fermi level will be equal to valence band to Fermi level in the bulk. So A equal to B. And what does it mean actually? So this is the mid gap in so this is the mid gap here, and this level also will bend, and so the difference in the bulk is equal to the difference in the surface, so C equal to D. So now what is the value of D? So C, our mid gap was in this position and this is the new position, so the total bending is C plus D. So if the total bending is C plus D, then the surface potential is phi st equal to, if this is Q phi b and C equal to D, then surface potential is twice of phi b, and that gives this equation. And from here we get the equation of threshold voltage, which is flat band voltage twice of this bending and plus this value. So now I would like to ask from where this value is coming from. So this is the oxide voltage. So you apply a voltage here, I see some voltage drop across the oxide, and then there is the flat band voltage and then the band bending. So all of this should be taken care of by the gate voltage, and when all of these are taken care of, then this voltage drop is called the Vt. And the condition for Vt is that the surface potential should be, or surface electron condition, electron concentration should be equal to the bulk hole concentration. Now this figure shows here the dependency of Vt on the TOX. So how does it affect TOX? So from the COX, so what is the value of COX? So it is epsilon by TOX. So in other words, the TOX, for this one we assume, or the authors in this book have assumed, this epsilon is SiO2. So TOX will be on here. So if I increase the TOX, my Vt will increase. So that's another strategy, I would say. When this is one strategy, so there is another dependency, that is the body doping density, but this is kind of under the square root. So you can see that the increase in Vt with this body doping is not that high. Rather, if we increase the TOX, our Vt will increase. So please keep this in your mind, that when you are trying to design something, then if you want to do some low voltage operation, then you want your devices to be turned on and off easily, so you have to reduce the TOX. And this is one aspect of scaling down, this reduction of TOX. But what will happen if you reduce the TOX, then there will be other issues which we will come to later at this point in this topic, when we'll be discussing this different scaling issues and the other related issues. Okay, so now we have reached the inversion. So what happens when we keep on increasing the voltage positively beyond threshold? So if we increase the voltage beyond threshold, as we know that we will reach an inversion layer, and inversion layer is characterized by the fact that the surface carrier concentration has been inverted. So that means in this area it looks like an N type, but it's only in the surface, and in the bulk it is P type. So this carrier concentration has been inverted. That's what we mean by inversion. So if we keep on increasing the voltage beyond inversion, then we will find that after some time is even if we increase the voltage by a mere 100 millivolt, we'll have a lot of electron concentrations, but that really doesn't happen. So a large VOX will appear in the oxide region, and that will soak up the voltage drop. That is, soak up the applied voltage. So which also means that phi s, that the value of um, surface potential, doesn't really increase beyond twice of phi b. And this also means our depletion region has reached its maximum value, so it doesn't really increase beyond that. So now our VG, how will it look like? So I have flat band voltage and twice of phi b, and then I will have the depletion charge and the voltage drop for the depletion charge, and also the voltage drop for the inversion charge. So if we all know that how this will look like, the depletion charge, and we have some rough estimate about the inversion, or even if we do not have, we can just assume that we have some inversion charges here. So this term is equal to Vt here, that is the threshold voltage. And now we are left with Vg equal to threshold voltage and subtracted by the voltage drop for the inversion charge. So it means that during the inversion layer, during the inversion operation, the strong inversion, the MOS capacitor just behaves like a capacitor, a parallel plate capacitor, and it is like the capacitance is COX, and the voltage drop is offset by the amount Vt. So now this is typically p-type substrate, and we will not have enough electrons to go for the strong inversion. So what does it happen? So that's why I told that MOS capacitor, it is fundamental, but it is not something that is widely used. So what we do, we just add two highly doped regions here, as we showed in the beginning, and then those are the N plus region, and they acts as the supplier of the rest of the electrons, so which we will learn eventually very soon. Well, now we have seen that this graph before. So the p-body transistor, that is the N-type MOSFET, that is shown here, that operates in the integrated circuit for the voltage from 0 to positive above. And what do we want? We want a smaller Vt, but not a smaller Vt, like below 1 volt, like 0 0.4, 0 0.3, but it should be larger than 0. So at 0 volt, there should not be any current. And this is called the enhancement type MOSFET, that does not have conduct at 0 volt. So there should not be any depletion region at Vg equal to 0. And then, but it should be small enough so that I do not have to apply a very large voltage to turn on the transistors. So that is why we always have to pair the p-body with N plus. So what happened when we pair p-body with p plus? Our the required voltage will be too high, maybe greater than 1 volt. We do not want that. So this is why we need to have the proper Vt, and to obtain proper Vt, the substrate and the gate doping should match. Should match, by the word I mean that p-body should be paired with N plus and N body should be paired with a P plus, not the other way around. Well, so let us review what we studied so far. So we start with the surface potential of the MOS capacitor, and we start with the point that is accumulation, and here is the flat band. So at flat band the surface potential is 0, and also we can neglect it in the accumulation region. Beyond flat band it starts to increase steadily, and it starts to increase, and once it reaches the threshold, it reaches the twice of the value of phi b when the channel is inverted and the inversion region starts, and then it stops increasing, it becomes constant. That's what we learned. So if we apply more voltage beyond Vt, then our oxide will soak up the voltage. Now here is the depletion region. So basically there is no depletion region in the left hand side of this flat band, because we are not applying enough positive voltage. So beyond flat band, if we apply more positive voltage, the channel starts to deplete, and after Vt there is no increase in the depletion region. Depletion region in MOS capacitor it is proportional to the band bending, or better to say the surface potential, and this is the maximum value of this depletion region. So now there are three charge components. There are three charge components in the MOS capacitor. One is the depletion charge, which is given by this equation, and the other one is the inversion charge, which is directly proportional to the oxide capacitance. And as we saw that in the inversion region, our MOS capacitor works as a parallel plate capacitor having an offset of Vt, and the other one is the accumulation charge. So when all of three are added together, this is the complete charge components of this MOS capacitor. So once we have this charge profile, we will be focusing on the MOS CV characteristics from our next class.